A distant swarm of galaxies holds secrets that could rewrite the laws of physics. This is the Hercules Cluster, a cosmic metropolis millions of light years away, where astronomers are uncovering phenomena that defy all explanation. We are about to embark on a journey through 25 of its most baffling mysteries, from galaxies that seem to be missing their invisible scaffolding to colossal structures that challenge our view of the entire universe. By the end, you will possess a new understanding of the profound puzzles at the very edge of human knowledge. We will confront a galaxy with no dark matter and a mysterious radio whisper that fills the void. How many cosmic rules are waiting to be broken? Deep within the Hercules Cluster, astronomers found a galaxy that simply should not exist. It defies one of the most fundamental rules of the cosmos, a rule so ingrained that its violation seems almost impossible. This galaxy appears to have no dark matter. For decades, we have believed that this invisible, mysterious substance forms the very skeleton of the universe, a hidden framework that holds galaxies together. Without its gravitational glue, a galaxy should fly apart, its stars scattered into the void. Yet here one is, spinning calmly, seemingly held together by nothing but its visible stars. The discovery sent shockwaves through the scientific community. How do you even measure something you cannot see? Astronomers used two trusted methods. They measured the rotation speed of the galaxy's stars. In a normal galaxy, the outer stars orbit so fast that the visible matter alone could not possibly hold them in place, implying a huge halo of dark matter is providing extra gravity. But in this strange galaxy, the stars moved exactly as you would expect if only the stars themselves were there. They also studied the motions of star clusters orbiting the galaxy, and again, the math pointed to the same astonishing conclusion. The mass was all accounted for by the glittering stars and gas. There was no room left for the dark scaffolding. This single observation challenges the standard model of cosmology at its core. If dark matter is universal, how did this galaxy form without it? The debate is fierce. Some suggest a violent past where a close encounter with another galaxy might have ripped its dark matter away. Others wonder if our methods are flawed or if we are misinterpreting the data. But the most thrilling possibility is that this galaxy is not an anomaly at all. It could be a sign that our fundamental theories about gravity and the cosmos are incomplete, that the universe has rules we have not yet begun to understand. The ghostly counterparts to that dark matter-deficient galaxy are scattered throughout the Hercules Cluster. These are the ultra-diffuse galaxies, cosmic phantoms as vast as our own Milky Way, yet containing only 1% of its stars. Picture a city the size of London, but with its lights spread so thin that the entire metropolis appears as a faint, shimmering haze against the blackness of space. That is the ethereal nature of an ultra-diffuse galaxy. They are so faint, so diaphanous, that for decades they simply blended into the background, invisible to our telescopes. Their discovery was a triumph of modern astronomy, a reminder of how much we still miss in the cosmic dark. The central mystery is one of survival. The Hercules Cluster is a violent, crowded metropolis where galaxies constantly jostle and collide. The immense gravitational forces at play should have ripped these fragile, wispy structures apart long ago. How did these ghostly giants endure in such a hostile neighborhood? Their very existence defies our expectations of galactic evolution. Astronomers are piecing together several compelling theories. One idea is that these are failed galaxies, islands that formed with incredibly dark matter-rich halos. This invisible, protective cocoon of dark matter could have acted as a powerful shield, its gravitational grip holding the delicate star field together against the cluster's chaos. Another hypothesis suggests a more tragic history. Perhaps they were once normal, star-forming galaxies that wandered too close to the cluster's heart. In this scenario, the intense gravitational tide stripped away their gas and dust, the raw materials for new stars, leaving behind only a pale skeleton of their former selves, a dispersed population of aging stars drifting silently through the void. The true answer likely lies in a combination of these ideas, a cosmic story of birth, protection, and loss written in the faintest ink imaginable. Even the ghostly galaxies of Hercules are dwarfed by a structure so vast it defies human comprehension. It is called the Hercules Corona Borealis Great Wall, a colossal filament of galaxies stretching across 10 billion light-years of space. To put that impossible distance into perspective, if you could travel at the speed of light, it would take you longer to cross this single structure than the current age of our planet Earth. This is not merely a cluster of galaxies, it is a continent of them, a sprawling cosmic metropolis that forms one of the largest things we have ever identified in the entire observable universe. Its discovery sent a tremor through the foundations of cosmology because its existence directly confronts one of our most cherished principles, the cosmological principle. This principle is a cornerstone of modern science, stating that on a very large scale, the universe should be homogeneous and isotropic. In simple terms, it should look roughly the same in every direction, a fairly uniform cosmic soup. But the Great Wall is a glaring exception. It is a monumental lump in the soup, a structure of such immense proportions that it should not be possible under our current models of how the universe evolved after the Big Bang. Finding a structure this big is like drawing a map of the Earth and discovering a single mountain range that spans from the North Pole to the South Pole. The scale is all wrong. It breaks the rules we thought were fundamental. The implications are staggering. If the cosmological principle is not as universal as we believed, then our entire understanding of the universe's origin and its large-scale structure may need a profound revision. What other colossal formations are waiting to be found, hidden in the deep fields of our telescopes, and what does it mean for our place in the cosmos if the universe is not the same everywhere, but is instead filled with such unimaginable and uneven grandeur? But the grandest structures are not always made of stars. Surrounding the very heart of the Hercules Cluster is an even more ethereal presence, a mysterious radio halo. This is not a collection of galaxies, but a faint, colossal cloud of radio waves that permeates the central region, a whisper from the void itself. This radio emission is a specific type known as synchrotron radiation. To understand what that means, picture the most powerful particle accelerator on Earth, but on a cosmic scale. This radio glow is created when high-energy electrons, particles moving at nearly the speed of light, spiral wildly through magnetic fields that are woven through the cluster's intracluster medium, the thin, superheated gas that fills the space between galaxies. The electrons are forced to change direction, and as they zigzag, they release energy in the form of these radio waves. The existence of the halo tells us two things for certain: that the cluster is filled with incredibly powerful magnetic fields and a sea of these ultra-fast electrons. But here is the profound mystery: what cosmic engine is powerful enough to create and sustain them? Where does the immense energy come from to keep this gigantic halo shining? The leading theories point to the violent life of the cluster itself. One idea is that the energy comes from the colossal mergers of entire galaxies, events that release unimaginable shockwaves through the intergalactic gas, accelerating particles to these fantastic speeds. Another suggestion is that the constant turbulent motion of the cluster's gas, stirred by the gravitational pull of all that dark matter, provides a more steady, continuous source of power. Yet, the exact mechanism remains one of astrophysics' great unsolved puzzles. This invisible, energetic shroud is a testament to the raw, untamed forces at work in what we might otherwise mistake for a quiet corner of space. At the center of one of these galaxies lies a gravitational monster that defies all expectations. This is an overmassive black hole, a cosmic paradox where the heart of the galaxy is far too heavy for its own body. Our current models suggest a tight, harmonious relationship between a galaxy and the supermassive black hole at its core. As a galaxy grows, so too should its central black hole, maintaining a kind of cosmic balance. But here, in the Hercules Cluster, that balance is shattered. This particular black hole is orders of magnitude more massive than it has any right to be, a giant inhabiting a house that seems far too small. How do you even weigh something that emits no light? Astronomers use the stars themselves as a scale. By meticulously tracking the orbits and velocities of stars whipping around the galactic center, they can calculate the immense gravitational pull required to hold them in such a frantic dance. The faster those stars move, the more mass must be locked away in the invisible central object. The numbers they found were staggering, pointing to a black hole of almost incomprehensible density. This discovery throws a wrench into our understanding of galactic evolution. If galaxies and their black holes grow together, how did this one become so lopsided? One compelling theory involves a violent history of galactic cannibalism. Perhaps this galaxy did not grow its own black hole to such an immense size. Instead, it may have devoured smaller neighbor galaxies over billions of years. With each merger, the central black holes would have spiraled together and combined, creating a single, ever more massive gravitational anchor. The galaxy itself might have been stripped of its outer stars during these chaotic encounters, leaving behind a relatively modest stellar body that belies the titan lurking within. Another possibility is that this black hole is a primordial relic, a rare leftover from the universe's chaotic infancy that formed with an enormous mass from the very beginning. Its existence forces us to reconsider the fundamental rules governing how cosmic structures form and interact. What other ancient giants are waiting to be found, hidden in plain sight at the hearts of seemingly ordinary galaxies? The mystery of that lone galaxy only deepens when we ask how it lost its dark matter in the first place. One compelling theory points to the brutal environment of the cluster itself. Imagine this galaxy on a perilous journey, swinging too close to the cluster's densely packed center. The immense collective gravity there could have acted like a cosmic thief, using tidal forces to rip the invisible dark matter halo away while leaving the more tightly bound stars relatively untouched. It is a form of gravitational stripping where the galaxy is robbed of its hidden mass. Another, more subtle idea suggests that dark matter itself was not stripped away but heated up. As the galaxy moved through the cluster, interactions with other dark matter halos could have transferred energy, scattering the particles into a much wider, more diffuse cloud that our current observations simply cannot detect. The dark matter would still be there, but its signal would be too weak to measure, effectively rendering it invisible to our instruments. Then there is the most radical proposal of all, one that questions the very laws of physics as we know them. What if dark matter does not exist at all? A theory known as modified Newtonian dynamics, or MND, proposes that our understanding of gravity is incomplete. Instead of invoking an invisible substance, MND suggests that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies. In this view, the stars in that strange galaxy are moving exactly as a revised law of gravity predicts they should, making the need for dark matter vanish entirely. Each of these explanations carries profound implications. Tidal stripping implies a violent cosmic history. Heated dark matter challenges our detection methods. But MND threatens to topple the entire foundation of modern cosmology. This single, dark matter-free galaxy is not just an oddity, it is a battlefield where competing visions of the universe are fighting for supremacy. This perfect ring of galaxies presents a puzzle of cosmic geometry. Scattered across the Hercules Cluster, these star systems form a near-circular structure so precise it seems almost artificial. The odds of such an arrangement happening by pure chance are astronomically low, forcing scientists to consider far more dramatic origins. Could this be the ghostly echo of a titanic collision? One leading theory suggests that two distinct groups of galaxies once slammed into each other in a catastrophic event. Picture two crowds of people running directly into one another. At the moment of impact, the outer edges would be flung outward, creating a temporary ring-like shape before everything collapsed back into chaos. In this cosmic scenario, the galaxies are like those people, flung outward by the immense gravitational shockwaves of the collision. We would be witnessing a single, frozen moment in a billion-year-long process, a ripple expanding through the fabric of space itself. Another possibility is that we are being fooled by perspective, that this is a line of sight illusion where galaxies at vastly different distances from us simply appear to align in a perfect circle against the dark canvas of space. To solve this, astronomers are turning to powerful statistical tools and sophisticated computer simulations. They run countless virtual universes, testing whether such a perfect ring can emerge from random distributions of galaxies. So far, the simulations suggest that chance alone is an unlikely architect. The ring holds its shape. The investigation is a race against time, for if this is indeed a collision remnant, the ring will not last. The powerful gravity of the cluster will eventually distort it, pulling the galaxies back into a more typical, shapeless cloud. This celestial circle may be a fleeting glimpse of the universe's immense capacity for both order and violence. What other ephemeral structures are we missing simply because they vanish in the blink of a cosmic eye? These runaway galaxies are cosmic fugitives, racing through the Hercules Cluster at speeds so immense they could break free from its gravitational grasp forever. We observe them on trajectories pointing straight out of the cluster like stones flung from a slingshot, destined for the lonely emptiness of intercluster space. The force behind this incredible acceleration is the cluster's own immense gravity. It acts as a vast, chaotic engine for these high-velocity ejections. When a smaller galaxy makes a close pass by the cluster's densely packed core or swings near a particularly massive galaxy, it can be caught in a complex gravitational dance. This is not a gentle push, but a violent transfer of energy, a gravitational slingshot that whips the galaxy away at a significant fraction of the speed of light. In a way, the cluster is playing a game of cosmic pinball with galaxies as the balls. The presence of these runaways is a direct testament to the Hercules Cluster's violent and dynamic history. It tells us that this metropolis of galaxies is not a serene, stable structure, but a place of constant, dramatic interactions. Each escaping galaxy is a fossil record of a past catastrophe, a close encounter that happened millions of years ago. By tracing their paths backwards, astronomers can piece together the cluster's stormy evolutionary timeline, identifying ancient collisions and near misses that shaped the galactic landscape we see today. What becomes of these ejected islands of stars? They are condemned to a solitary future, drifting through the cosmic voids where resources for new star formation are scarce. They will slowly fade, their stellar populations aging into a quiet, red gloom. Their frantic escape is a one-way ticket to a silent and isolated fate. Even the superheated gas between the galaxies holds its own sharp-edged secrets. Winding through the heart of the Hercules Cluster are vast, wave-like structures called cold fronts. Seen in X-ray light, these are not walls of ice in the void, but immense boundaries where different regions of the cluster's atmosphere meet. On one side of the front, the gas is denser and slightly cooler. On the other, it is hotter and more diffuse. It is the cosmic equivalent of a distinct weather front in Earth's atmosphere, where a mass of cold air pushes against warm air, creating a sharp dividing line. The profound mystery is not their existence, but their incredible longevity. The intracluster gas is a turbulent, chaotic sea, constantly stirred by the motions of galaxies and the echoes of ancient collisions. In such a violent environment, any sharp boundary should be blurred and smeared away by turbulence in a relatively short cosmic time, perhaps just a few 100 million years. Yet these cold fronts persist for billions of years. their edges remaining razor-sharp across distances that dwarf entire galaxies. How can such crisp structures survive the constant cosmic churning? The leading theory involves the stabilizing power of magnetic fields. Imagine the thin, hot gas is threaded with invisible magnetic lines, like a fluid filled with countless elastic bands. As a cold front plows through this medium, these magnetic fields could be stretched and draped tightly around the leading edge, forming a protective sheath. This magnetic layer would act as a barrier, suppressing the turbulent mixing that would normally destroy the sharp temperature divide. It would be like a layer of oil on water, preventing two liquids from readily blending. Another possibility points to the nature of the gas flow itself. If the dense gas is moving through the cluster in a very smooth, laminar flow, much like a knife cutting through water, it could potentially maintain its coherent shape for eons. The survival of these sharp fronts is a silent witness to the delicate, invisible forces shaping the cosmos. It suggests a level of order hidden within the apparent chaos, a reminder that even in the most violent places, the universe can still draw a perfect, unwavering line. Amidst the brilliant stellar cities, a different kind of phantom has emerged. Radio telescopes have pinpointed a massive, swirling cloud of hydrogen gas, a beacon in the invisible spectrum that holds enough raw material to build an entire galaxy. Yet, when astronomers point their most powerful optical telescopes at the same patch of sky, they find nothing but empty darkness. There are no stars. This is the dark galaxy candidate, a ghost of pure potential drifting through the cluster. The sheer mass of the hydrogen cloud is the core of the mystery. Simple calculations show that a gas cloud of this size should have collapsed under its own gravity long ago, triggering the birth of millions of stars. The fact that it remains dark and starless suggests something is holding it back, or that its true nature is not what it seems. Three compelling possibilities are on the table, each with dramatic implications. The first and most thrilling idea is that this is indeed a true dark galaxy, a cosmic object dominated not by stars but by dark matter. In this scenario, the invisible dark matter halo is so massive and so spread out that its gravity prevents the gas from condensing densely enough to ignite stars. It would be a galaxy that failed to light up, a monument to the hidden mass that shapes our universe. The second, more destructive theory argues this is no independent galaxy at all. It could be a vast tidal tail, a streamer of gas violently torn from a larger, star-filled galaxy during a close encounter. The gravitational forces of a near collision can stretch a galaxy, pulling its gas out into long, faint ribbons that linger for eons. We would be seeing the cosmic aftermath of a galactic assault, a scar left in intergalactic space. The third possibility reaches back to the dawn of time. This could be a primordial cloud, a relic from the early universe that has somehow remained pristine and undisturbed for billions of years. It is a pocket of the ancient cosmic gas that never felt the trigger to begin the process of star formation, a sleeping giant that never awoke. Confirming its true identity is an immense observational challenge. How do you prove the existence of something defined by its absence? Astronomers search for any faint, telltale glow of stars within the cloud, even just a handful, which would tilt the scales toward the tidal debris theory. They also study the cloud's motion and rotation, looking for the distinctive signature of a stabilizing dark matter halo. If the gas is swirling in a way that cannot be explained by its visible mass alone, it would be powerful evidence for a dark galaxy. This cosmic question mark forces us to confront the very definition of a galaxy. Must it be a collection of stars, or can it be a gathering of gas and dark matter alone? The answer, hidden in that dark patch of sky, could reveal an entirely new class of cosmic object. Their survival hinges on a delicate balance of cosmic forces. For these ghostly giants to endure the cluster's rough neighborhood, they must possess some form of incredible, unseen armor. One of the strongest theories is that they are, in fact, cosmic fortresses protected by an immense concentration of dark matter. While they appear wispy and fragile, their invisible dark matter halos could be incredibly dense and widespread. This halo would act as a powerful gravitational shield, its immense mass binding the few stars together with an unbreakable grip. The galaxy would be like a featherweight boxer with an impenetrable defense, able to absorb the gravitational blows of passing galaxies without being torn apart. Another compelling idea casts these ultra-diffuse galaxies as cosmic yo-yos, known to astronomers as backsplash galaxies. In this scenario, a galaxy falls into the cluster's immense gravitational well, gaining tremendous speed as it plunges toward the crowded core. But instead of settling there, it swings around the dense center and is flung back out toward the cluster's outskirts, like a slingshot maneuver on an unimaginable scale. This violent journey would have stripped away its gas and dust, quenching star formation and leaving behind only the old red stellar population we see today, a galaxy that was processed and then ejected. A third possibility is that they are quiet introverts thrust into a chaotic party. These galaxies may have formed in the serene isolation of intercluster space, far from the gravitational turmoil of a dense cluster. There, in the cosmic quiet, they could have evolved slowly into their large, diffuse forms. Only later were they captured by the growing Hercules Cluster, dragged into the metropolis against their will. Their pre-existing, spread-out structure allowed them to survive the capture, even as their star-forming lives came to an abrupt end. Each of these survival strategies paints a different portrait of cosmic history. Are these galaxies the heavily armored knights of the dark matter world, the lucky survivors of a gravitational slingshot, or the quiet outsiders assimilated into the cosmic crowd? Their continued existence is a testament to the diverse and unexpected paths a galaxy can take. This isolated cloud of hydrogen is a cosmic orphan, drifting through the void with no stellar family to call its own. Discovered by its faint radio whisper, this vast reservoir of neutral hydrogen gas holds the raw material for billions of stars, yet it floats in complete isolation, untethered to any known galaxy. Its very existence challenges our understanding of where matter resides in the universe and how galaxies gather their building blocks. The central puzzle is its origin. Where did this solitary cloud come from? One compelling theory paints a picture of cosmic violence. It could be the scattered debris from a galactic collision, a long, faint ribbon of gas torn from a larger galaxy during a close encounter millions of years ago. This would make it a ghostly scar, a testament to a past gravitational assault that left this material stranded in intercluster space. Another, more profound possibility is that we are looking at a failed galaxy. In this scenario, the cloud did indeed begin to coalesce, gathering a huge halo of dark matter around it. But for some unknown reason, the trigger for star formation never fired. The gas simply never condensed enough to ignite, leaving behind a dark, sleeping giant composed almost entirely of primordial hydrogen and its invisible dark matter anchor. A third, simpler idea suggests the cloud is condensing directly from the intergalactic medium itself, a random knot of gas slowly accumulating from the thin, superheated plasma that fills the space between galaxies. Each origin story carries immense significance for the grand Baryons cycle of the universe. Baryons are the ordinary matter that makes up stars, planets, and us. Theorists have long predicted that vast reservoirs of this normal matter should be floating in the cosmic web, but much of it has remained missing from our observations. This anomalous cloud could be a crucial piece of that puzzle, a direct detection of the warm, hot intergalactic medium that models say should be there. If such clouds are common, they could represent the hidden backbone of cosmic structure, the unseen reservoirs from which galaxies continually draw their fuel. Finding this lone cloud forces us to ask how many other such invisible islands are drifting in the darkness. and what their silent presence means for the story of how a universe filled with raw potential becomes one glittering with light. Gravity itself becomes a lens in the Hercules Cluster, warping the fabric of space to magnify the light from galaxies billions of light years behind it. This cosmic trick, called gravitational lensing, allows us to see farther into the universe than ever before. Yet here, the lens is flawed. The distortion it creates is subtly wrong. The way it bends the light from these distant background galaxies does not perfectly match the map of mass we have constructed from all the visible stars and the inferred dark matter. It is as if you looked through a magnifying glass and found its curve was uneven, warping the image in ways the glass's shape cannot explain. This is the lensing anomaly, a mismatch between the cosmic blueprint and the final construction. The possibilities behind this discrepancy are as profound as they are puzzling. One leading idea is that our map of the cluster's mass is simply incomplete. We might be missing a complex substructure of dark matter, smaller, denser clumps of the invisible material that are hidden between the galaxies. These unseen clumps would exert their own gravitational pull, subtly altering the lensing effect in localized areas without giving off any light we can detect. It would be like trying to understand the shape of an iceberg by only looking at the tip, missing the hidden structures beneath the surface that change how the water flows around it. Another, more radical possibility challenges the laws of physics themselves. What if our understanding of gravity is incorrect on these immense scales? The theory of general relativity has passed every test we have thrown at it for over a century, but the Hercules Cluster presents a unique laboratory, a region of space with a gravitational field unlike any we can replicate. Perhaps in such extreme environments, gravity behaves in a way that our current equations do not fully capture, creating a lensing effect that appears anomalous only because our model is imperfect. This single imperfection in the cosmic lens forces us to question what we think we know about the universe's hidden architecture. Is the discrepancy a sign of missing matter, or a flaw in our most fundamental theory of how matter shapes space and time? The answer is written in the distorted light of galaxies far beyond our own. A brilliant beacon shines from the very edge of the observable universe, its light piercing straight through the heart of the Hercules Cluster on its 10 billion-year journey to Earth. This is a quasar, the intensely luminous core of a distant galaxy, powered by a ravenous supermassive black hole. Normally, such a cosmic lighthouse offers a clean, predictable signal. But this one is different. As its light filters through the cluster's vast atmosphere of hot gas and dark matter, it emerges with a strange and unexpected signature imprinted upon it. The quasar's spectral lines, the unique chemical fingerprints in its light, are subtly distorted in a way that defies simple explanation. It is as if the cluster itself is adding an unknown ingredient to the mix, altering the light in a manner our models of the intracluster medium cannot account for. The leading theory points to the thin, superheated plasma that fills the space between the cluster's galaxies. This gas is known to contain heavy elements forged in the hearts of ancient stars and scattered by supernova explosions. Yet the specific pattern of absorption and distortion seen in the quasar's light suggests a composition or a physical state that is unlike anything we have observed elsewhere. Perhaps vast, unseen reservoirs of cool, dense gas are floating within the hot medium, their presence only revealed when the brilliant quasar backlights them. Or maybe the magnetic fields that thread through the void are far more complex and powerful than we thought, capable of twisting the light in new and unrecognized ways. An even more exotic possibility involves the dark matter itself. Could the spectral anomaly be a faint trace of an interaction between light and the invisible particles that dominate the cluster's mass? While highly speculative, the idea that we might be seeing a secondary effect of dark matter, a shadow of its influence on the fabric of spacetime itself, is a tantalizing prospect. This single quasar, a pinprick of light from the cosmic dawn, has become a probe for the deepest secrets of the cluster it passes through. Its anomalous glow challenges us to reconsider the true nature of the space between galaxies, a space we are learning is far from empty. Even the inventory of the cosmos has a major accounting error. We can calculate with astonishing precision how much ordinary matter the Big Bang should have produced, the protons and neutrons that make up every star, planet, and person. Yet when we tally up all the visible objects in the universe, from the brightest galaxies to the faintest gas clouds, we come up short. A huge portion, perhaps as much as half of all the normal matter, is simply missing. This is the missing baryon problem, and the Hercules Cluster is a key crime scene in this cosmic investigation. The leading suspect for this hidden matter is a ghostly network of incredibly diffuse, superheated gas known as the warm-hot intergalactic medium, or WIM. This is not a cold, dark void, but a seething web of plasma filaments, a cosmic fog so thin it is nearly impossible to see. The Hercules Cluster, with its immense gravitational well, acts as a natural trap for this elusive material. As the WIM flows along the cosmic web and falls into the cluster, it gets compressed and heated to millions of degrees, causing it to glow faintly in X-ray light. By studying this X-ray halo with space-based observatories, astronomers are essentially taking a census of the ordinary matter that has been captured. But the plot thickens when we use the cluster's own gravity as a scale. The total mass of the cluster, measured by how it bends light from distant galaxies, tells us one number. The mass of the hot gas we can see in X-rays tells us another. The difference between them is the dark matter, but the amount of hot gas itself is a crucial piece of the puzzle, a direct measurement of the ordinary matter present. If the amount of gas we detect in the Hercules Cluster matches the universal predictions for baryons, then the mystery is solved, and the missing matter was hiding in this hot, diffuse fog all along. If it does not, then the search must continue deeper into the voids. This makes the cluster a fundamental calibration point for the entire universe. Its hot atmosphere is a test tube holding the answer to a question that defines our cosmic composition, revealing whether we have finally accounted for every atom or if a deeper, more profound mystery still awaits us in the spaces between. The shapes of galaxies themselves tell a secret history of violence and isolation. In most massive clusters, a predictable pattern emerges, dominated by featureless, red, elliptical galaxies, the cosmic retirees that have used up their gas and ceased forming stars. But the Hercules Cluster breaks this mold with an unusual and puzzling mix of shapes. It holds both a surprising number of spiral galaxies with their delicate, star-forming arms and a curious collection of odd, distorted galaxies that defy easy classification. This abnormal morphology is a direct challenge to our understanding of how galaxy clusters evolve. The environment of a dense cluster is a galactic pressure cooker. The primary engine for transforming a vibrant, gas-rich spiral into a quiescent elliptical is a process known as galaxy harassment. This is not a single, catastrophic collision, but a death by 1,000 cuts. As a spiral galaxy orbits through the crowded cluster core, it experiences countless rapid, close gravitational encounters with other galaxies. Each pass tugs and twists at its structure, stripping away its loose outer gas and dynamically heating its stellar disk. Over time, these repeated gravitational shocks rob the galaxy of the ordered motion that defines its spiral arms, puffing it up into a more chaotic, ball-shaped elliptical. The presence of so many surviving spirals in Hercules suggests its pressure cooker may not have reached a full boil. Perhaps the cluster is younger than others of its mass, and this transformation process is still ongoing, leaving us with a snapshot of cosmic evolution in progress. Alternatively, the cluster's overall structure might be less centralized, with vast regions where galaxies can orbit without experiencing the intense harassment needed to destroy their delicate forms. The strange, distorted galaxies caught in mid-transformation are the key evidence. They are the missing links showing us the violent process in action, as gravitational tides stretch them into bizarre, tadpole-like shapes or rip long tails of stars from their bodies. This unusual menagerie of galactic shapes forces astronomers to recalibrate their models. It reveals that the journey from a spiral to an elliptical is not a single, uniform highway, but a complex network of backroads and detours, heavily influenced by the specific, chaotic history of the cluster itself. What other stories of cosmic survival are written in the twisted forms of these island universes? Astronomers are now hunting for the engine behind this colossal radio shroud. The leading suspect is a process known as re-acceleration. Imagine the cluster's vast sea of gas as an ocean still churning from a past storm. When entire galaxy groups collide, they send immense shockwaves rippling through this intergalactic medium. These merger shocks act like natural particle accelerators, giving a fresh boost of energy to ancient, slower-moving electrons, forcing them to spiral at near-light speed once more and rekindling the radio glow we detect. It is a cosmic echo of a long-finished cataclysm. A competing theory proposes a more continuous power source, secondary emission. In this model, the real powerhouses are cosmic ray protons, which are incredibly stable and can linger for billions of years. When these protons occasionally collide with other particles in the thin gas, the impacts create a shower of new, high-energy electrons right there on the spot. This process would act like a steady drizzle of power, constantly replenishing the radio halo without needing a recent, violent merger to trigger it. A third, more elusive possibility is that we are being fooled by the combined light of countless faint radio galaxies, each too dim to see individually but together creating a false, uniform glow. To solve this, observational campaigns are using the world's most sensitive radio telescopes in a new way, not just to take a picture, but to listen for a specific texture in the radio signal. They are searching for tiny, localized fluctuations in the halo's brightness. A halo powered by merger shocks would have a clumpy, uneven structure, while one fed by secondary emission should be remarkably smooth. Finding that subtle graininess would point directly to a past collision as the culprit. This is not just about identifying a power source, it is about learning to read the energetic history of the entire cluster from its faintest whisper. The answer will reveal whether this halo is the dying breath of a forgotten impact or the steady hum of an invisible particle engine. Woven through the Hercules Cluster are faint, celestial rivers of stars, flowing in graceful arcs between the brilliant galaxies. These are stellar streams, the ghostly remains of dwarf galaxies that ventured too close to the cluster's immense gravitational pull and were slowly, methodically torn apart over billions of years. Their very existence is a record of cosmic cannibalism on a grand scale. Yet some of these streams are not the smooth, predictable ribbons our models expect them to be. Instead, they show bizarre kinks, sudden gaps in their stellar flow, and strange variations in density, as if an invisible hand has reached into the river and churned the waters. A perfectly smooth stream would tell a simple story of a steady, relentless tidal force. These distorted streams, however, suggest a far more chaotic and violent past. The primary suspect for these disruptions is the unseen architecture of the cluster itself, specifically dark matter subhalos. Our models predict that the massive halo of dark matter enveloping the entire cluster should be littered with smaller, denser clumps of this invisible material. These subhalos would be like hidden boulders in a flowing river of stars. As a stellar stream passes near one, the subhalo's gravity would give the stars a sharp, localized tug, punching a hole in the stream or warping its path into a strange bend. Finding these kinks and gaps is therefore like a cosmic game of connect the dots, allowing astronomers to map the invisible dark matter substructure by reading the scars it leaves on the visible stars. But the story may be even more complex. Some of the distortions might not be from a single event, but from the cumulative effect of multiple close encounters with other galaxies, each one adding another gravitational nudge that further twists the stream. Or perhaps the dwarf galaxy that was shredded was itself unusually dense or had a complex internal structure, leading to a more lumpy and uneven debris trail as it came apart. Each distorted stream is a unique fossil, a tangled thread that, when unraveled, can reveal a detailed history of the cluster's formation and the hidden distribution of its dominant dark matter component. These faint rivers are more than just relics of destruction. They are the most delicate traces we have for the universe's greatest unseen influence. What other secrets about the dark cosmos are written in these twisted strands of light? Each of these formation pathways for the overmassive black hole rewrites a different chapter of cosmic history. The most ancient possibility is the direct collapse black hole. In the universe's first chaotic moments, vast clouds of pristine hydrogen could have collapsed under their own weight so violently that they bypassed star formation entirely, instead forging a single, monstrous black hole seed with a mass thousands of times greater than the Sun. This primordial giant would have had a colossal head start, feasting on the surrounding gas for billions of years to become the behemoth we see today. It would be a living fossil from the cosmic dawn, a relic from an era when the universe operated by different, more extreme rules. A second, more exotic theory involves dark matter in a uniquely potent form. If the black hole formed at the center of an unusually dense knot or spike of dark matter, the particles could have annihilated each other, releasing a torrent of energy that fed the black hole's growth with incredible efficiency. This dark matter engine would have provided a steady, powerful fuel source, allowing the black hole to swell to an immense size even in a galaxy with relatively little ordinary gas to consume. The third scenario is one of cosmic gluttony. Perhaps this black hole was not always so overmassive. During a major galactic merger, vast rivers of gas would have been funneled directly into the galactic center, triggering a hyper-efficient feeding frenzy. The black hole would have gorged itself, growing rapidly to its enormous present mass in a relatively short, violent burst. The feast then ended, leaving the galaxy stripped and quiescent, its stellar body unable to match the scale of the monster it now hosts. Each pathway leaves a different fingerprint on the black hole and its surroundings. A direct collapse seed would be incredibly ancient, its history written in the ages of the surrounding stars. A dark matter spike would influence the motions of stars near the galactic center in a unique way. The evidence of a past feeding frenzy might be found in the chemical composition of the galaxy's remaining gas. Determining which story is true forces us to look deeper into the heart of this galaxy, searching for the faint echoes of the processes that built a Titan. The relentless growth of the Hercules Cluster unfolds before our eyes in the silent fall of galaxy groups. We are witnessing entire families of galaxies, small clusters in their own right, being drawn by immense gravity into the cluster's sprawling metropolis. This cosmic accretion is how all great clusters build their mass, yet the process is far from the smooth, predictable inflow our simulations often suggest. Observations reveal these infalling groups as chaotic and unpredictable, their gas being ripped away in strange, asymmetrical patterns and the galaxies within them responding in ways we never anticipated. One of the most startling observations is how the hot gas within these groups is stripped. As a group plunges into the main cluster's dense atmosphere, it should experience a steady, uniform pressure that peels the gas away smoothly, like a steady wind blowing smoke from a chimney. Instead, we see the gas being torn off in clumps and shreds, creating turbulent wakes that suggest a far more violent and messy interaction. It is as if the cluster's atmosphere is not a uniform blanket, but a chaotic sea with unpredictable currents and whirlpools. The galaxies themselves are not passive passengers on this doomed journey. Within these infalling groups, we see galaxies that have had their star formation violently quenched, their gas reserves stripped before they even reach the cluster's core. Others, paradoxically, show brief, intense bursts of new star birth, as if the immense pressure of the infall is violently squeezing their remaining gas and triggering a final, glorious flurry of stellar creation. This makes the infalling groups a unique real-time laboratory. We are not just looking at a static structure, we are watching the Hercules cluster actively feeding, a process that shapes its evolution moment by moment. Each erratic group tells a different story about the density of the intracluster medium it is penetrating, the strength of the magnetic fields it encounters, and the complex interplay between gravity and hydrodynamic forces. By studying these messy, real-world examples, astronomers are forced to refine their models of cosmic structure formation, revealing that the universe's growth is a far more turbulent and dramatic affair than we ever imagined. The chemical makeup of the Hercules cluster tells its own troubled story. When astronomers measure the hot gas between the galaxies, they find a puzzling inconsistency in its metallicity, a term scientists use for the abundance of elements heavier than hydrogen and helium. This is the cosmic fingerprint of stellar life and death, the residue of countless supernova explosions that have forged heavy elements and scattered them across space. Yet the pattern of these elements is all wrong. The measurements reveal unexpected pockets of gas that are either surprisingly rich in iron and oxygen or strangely deficient, creating a chaotic chemical map that does not match the smooth, well-mixed distribution our models predict. It is as if a painter, instead of creating a uniform wash of color, had splattered the canvas with random, intense dabs of pigment. These heavy elements are born in the hearts of massive stars and are only dispersed into the universe when those stars die in violent supernova explosions. For billions of years, this process of chemical enrichment should have thoroughly mixed the cluster's atmosphere, like stirring cream into coffee. The fact that we still see such sharp variations means the mixing has been far less efficient than anyone thought. One explanation points to the cluster's violent history of galactic mergers. When two smaller groups of galaxies collide to form a larger cluster, they bring together separate reservoirs of gas, each with its own distinct chemical history. Instead of blending seamlessly, these different chemical soups might remain partially separate for eons, their boundaries preserved by magnetic fields or by the sheer, turbulent chaos of the collision itself. We could be seeing the still unmerged ingredients of a cosmic recipe. Another possibility challenges our understanding of the supernova themselves. Perhaps the types of stars that exploded in the cluster's early galaxies were different from what we see today, producing a different ratio of heavy elements that leaves a signature we are only now learning to read. Or maybe vast, cool gas clouds are condensing from the hot medium, selectively trapping certain elements and creating localized chemical deserts and oases. These anomalous metallicities are more than just a chemical curiosity. They are a direct record of the cluster's most violent and creative moments. Every unexpected concentration of iron is a fossilized echo of a stellar catastrophe that occurred billions of years ago. By decoding this messy chemical map, we are reading the autobiography of the Hercules cluster, a story written not in words but in the elemental ashes of dead stars. This faint cosmic afterglow is the ghost of the cluster's violent history. Drifting between the brilliant galaxies is an incredibly dim, pervasive light, a shimmering haze known as intracluster light. It is the collective glow of countless stars that have been violently evicted from their home galaxies, now wandering the intergalactic void as permanent orphans. These stars were ripped away during close gravitational encounters, their celestial citizenship revoked and cast into the darkness. For this light to be visible at all across such vast distances means we are seeing the combined output of trillions of these lost suns, a phantom metropolis woven between the shining cities. But the story deepens where this light is not smooth and uniform. Astronomers have mapped regions where the glow becomes strangely clumpy, gathering in faint, swirling pools and tendrils. Other areas show an unusual color, a hue that is redder or bluer than the ambient starlight. This is not a random distribution, it is a forensic snapshot. A smooth, even glow would suggest a long, steady history of galactic harassment, a slow and continuous trickle of stars into the void. Clumps and distinct colors, however, are the signature of something far more specific and dramatic. A patch of unusually blue light points to a recent and catastrophic event. Blue stars are massive, hot, and short-lived. Their presence in the intracluster light means they were torn from their galaxies recently, in cosmic terms, before they had time to burn out. This is the fresh debris from a single major galactic collision, a specific wreck we can pinpoint in time. Conversely, a region of redder light tells a different tale. It is composed of older, cooler stars, the survivors of a disruption that happened billions of years ago, a fossilized crime scene preserved in the faintest of glows. These stellar orphans are more than just spectral evidence, they are tracers of the cluster's invisible skeleton. They are not bound to any single galaxy, so their motion is governed solely by the cluster's overall gravitational field, which is dominated by dark matter. By tracking the subtle movements of this ghostly light, astronomers can literally weigh the cluster's dark matter halo in a way that is independent of other methods. Each clump and every strange color is a chapter in a violent biography, written in a script of lost suns. What other forgotten collisions are recorded nowhere else except in this dim, collective memory of the stars? Even the most energetic light holds its secrets close. The Hercules Cluster should be a powerful beacon of gamma rays, the highest energy form of light in the universe, yet it remains strangely quiet. This silence is a profound puzzle in itself. Galaxy clusters are natural particle accelerators on a cosmic scale, filled with cosmic rays, which are atomic fragments traveling at nearly the speed of light. When these cosmic rays collide with the protons in the thin, hot gas between the galaxies, or with the faint glow of ancient light left over from the Big Bang, they should produce a predictable shower of gamma rays. We see this process elsewhere, but in Hercules, the expected gamma-ray glow is either absent or so faint it defies our detection. This missing signal forces us to rethink the invisible forces at work within the cluster. The leading theory points to the cluster's powerful magnetic fields. These invisible lines of force woven through the space between galaxies could be acting as a cosmic cage. When a cosmic ray is produced, instead of flying freely to create a gamma ray far away, it becomes trapped by these magnetic fields. The particle is forced to spiral endlessly along the magnetic lines, its path a tangled corkscrew that prevents it from escaping the cluster. From our distant vantage point, this would make the gamma ray emission appear incredibly faint and diffuse, spread over such a vast area that it blends into the background noise of the universe. Another possibility is that the process of particle acceleration within Hercules is simply less efficient than we thought. The shockwaves from galaxy mergers or the turbulence in the gas might not be imparting enough energy to create the quantity of high-energy cosmic rays needed to produce a strong gamma-ray signal. This creates a direct conflict with other observations, like the presence of the giant radio halo. That halo requires a sea of high-energy electrons, which often originate from the same violent events that accelerate cosmic ray protons. How can one type of particle be accelerated efficiently enough to create a vast radio shroud, while the other type remains so scarce that gamma rays are almost absent? This high-energy mystery is not just about a missing light. It is a crucial test for our understanding of the cluster's most fundamental physics, forcing us to measure the strength of its invisible magnetic cages and the true power of its hidden cosmic engines. The spiral galaxies of Hercules spin to a rhythm we do not fully understand. Each one is a vast pinwheel of stars and gas, and by charting the orbital speeds of these components from the core to the outer edges, astronomers create what is known as a rotation curve. In a universe governed only by the gravity of visible matter, we would expect a very specific pattern. Stars close to the luminous center, where most of the mass is concentrated, should orbit very fast. But as you move further out into the sparse galactic suburbs, their speed should drop off sharply, just as the outer planets in our own solar system orbit the Sun more slowly than the inner ones. This is not what we see. For decades, observations have shown that the rotation curves of most spiral galaxies remain flat far out into their dim outskirts. The outer stars race around just as fast as the inner ones, implying the presence of a huge, invisible mass, a dark matter halo, whose gravity grips the entire structure. This is the established rule, yet within the Hercules Cluster, that rule is being bent. Some of its spiral galaxies show rotation curves that are not perfectly flat. They exhibit subtle but significant deviations, kinks, or unexpected dips in the orbital speeds of their outer stars. These anomalies are a direct challenge. If every galaxy is embedded in its own universal, fluffy halo of dark matter, its rotation curve should be smooth and flat. The presence of these wrinkles suggests the cluster's extreme environment is interfering. One compelling theory is that the cluster itself is stripping away the outer parts of these dark matter halos. As a spiral galaxy orbits through the crowded cluster core, the combined gravitational pull from hundreds of other galaxies and the vast sea of intracluster dark matter could be shearing off the outermost, least bound particles of its invisible halo. This would effectively truncate the dark matter distribution, robbing the galaxy's outer edges of the gravitational anchor that keeps stars orbiting at high speed. The result would be a rotation curve that begins to fall away at the edges, a telltale sign of environmental tampering. Another possibility is that we are seeing the dark matter being heated up. Gravitational interactions with other dark matter clumps could be transferring energy, causing the particles to move faster and spread out into a larger, more diffuse cloud. This would weaken the gravitational pull in the galactic suburbs, again causing the rotation speeds to drop. Then there is the more radical interpretation. Perhaps these anomalous curves are not caused by the manipulation of dark matter, but are evidence that dark matter does not exist at all in its current theoretical form. Could the unique gravitational field of the entire cluster be influencing the dynamics of these spirals in a way that modified gravity theories can explain, but the standard model of dark matter cannot? Each twisted rotation curve is a silent witness to a cosmic struggle, a tug of war between a galaxy's intrinsic properties and the overwhelming influence of its metropolitan home. Deep within the radio whispers of the Hercules Cluster, astronomers are listening for the universe's most precise timekeepers' pulsars. These are the lighthouses of the cosmos, the collapsed cores of massive stars that exploded long ago. Each one is a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. As they spin at incredible speeds, they beam out pulses of radiation with a regularity that rivals atomic clocks. Finding these cosmic metronomes in the cluster is like searching for a single, specific heartbeat in a roaring stadium. Their rhythmic pulses offer more than just precise timing. They are exquisite tools for probing the very space they travel through. The clock-like regularity of their pulses means any detected delay or distortion is a clue, a fingerprint left by the material between us and the pulsar. One of the most telling measurements is the dispersion measure. As a pulsar's signal journeys across millions of light years, the electrons in the thin gas of the intracluster medium subtly slow it down. Lower frequency radio waves arrive just a fraction of a second later than their higher frequency counterparts. By measuring this delay, astronomers can calculate the total number of electrons the signal has encountered, effectively taking a census of the invisible ionized gas that permeates the cluster. But some pulsars in Hercules tell a strange story. Their dispersion measures are unexpectedly high, suggesting they are shrouded in pockets of unusually dense intracluster plasma. This could mean the gas within the cluster is not smoothly distributed at all, but is instead clumped and tangled in ways our larger-scale observations have missed. Other pulsars have been found spinning at rates that defy easy categorization, with periods so extreme they challenge our models of how neutron stars form and evolve in such a dense environment. Could they be the rare products of a unique stellar collision within the cluster, or are they ancient pulsars that have been spun up to incredible speeds by accreting material from a binary companion? Each anomalous pulse is a coded message, a direct sampling of the cluster's hidden conditions. By deciphering their rhythms, we are not just cataloging dead stars, we are mapping the invisible currents of a cosmic ocean. From missing dark matter to ghostly galaxies that defy destruction, from colossal walls that break the cosmological principle to the mysterious radio whispers that fill the void, the 25 unexplained phenomena of the Hercules Cluster form a cosmic puzzle box of unparalleled complexity. Each mystery, from the overmassive black holes to the distorted stellar streams and the anomalous gamma-ray silence, chips away at the foundations of our understanding. This celestial metropolis is not merely a collection of stars. It is a living laboratory where the fundamental laws of physics, gravity, and cosmic evolution are being tested and rewritten in real time. The cluster forces us to confront the limits of our knowledge, showing us that the universe is far stranger, more dynamic, and more mysterious than we ever dared to dream. So the next time you gaze up at the night sky, remember that hidden in the darkness between the visible stars are enigmas waiting to be solved. Let the enduring mystery of the Hercules Cluster be a reminder to always stay curious, for the next great discovery, the one that changes everything, could be just one observation